Hi, and welcome to our final webinar before we take a break for the summer. And today we have Raoof Gholami, who's going to speak with us. So I will hand it over to him. Thanks.
Okay, thank you, Lisa. So thank you guys for joining and being with us. So here we go with the presentation about the hydrogen economy. I will go through the hydrogen economy and the challenges of that, and then I will go a bit deeper about the larger scale energy storage and the challenges that we have there. Okay, so let's go for it. Let's start with the cliche, the temperature rise. So we know that the CO2 concentration of the greenhouse gases in the atmosphere is increasing, and eventually the temperature is rising, and climate change is happening. So there have been a lot of discussion around this, and then we had a lot of kind of a conclusion that perhaps the natural sinks can take care of the greenhouse gases. So when we say natural sinks, we are basically talking about the ocean, atmosphere, and the forest. I mean, they have the capacity to capture the CO2. But then if you look at the plot on the right side, you will see that the amount of emission from the fossil fuels and the land degradation that we have made has basically make it impossible for the natural sinks to take care of the emission. So, and then one thing that we need to remember is that the ocean has already reached its budget, so it doesn't really have that much of capacity to absorb more. And then the forest basically, if you have any kind of wildfire for the forest, all of the CO2 that being captured by the trees will be released back to the atmosphere. So natural sinks doesn't seem, I mean, they would help, but doesn't seem to be the solution to the greenhouse gas emission and climate change. Then we look at the alternatives, coming up with the renewable energy, phasing out the fossil fuels, but then most of the renewable energy have their own kind of challenges. With the wind and solar, we have the intermittency. Geothermal, not everyone has it. Nuclear power has the public acceptance. So, I mean, while we are struggling with those kind of renewable energies, we decided to go with the CCS. So carbon capture and storage can be a solution. So it can be part of the energy mix. It will give us a bit of time to still use the natural gas or other fossil fuels while we are working on the renewable energy. But then CCS has its own kind of challenges. It's extremely expensive, especially the capturing part. The government needs to put a lot of incentives, and then the companies are not completely happy to look at this energy intensive CCS technology. So then eventually we came up with the idea that shall we go with the hydrogen as a economy as a solution for all of these challenges. What is the hydrogen economy? Is basically producing hydrogen and feeding hydrogen to everyone. It can be the industries, it can be the aviation system, the light duty trucks, the heavy duty trucks, the households. So basically the whole economy will be covered by the hydrogen. And hydrogen is a clean energy carrier, is it? So if you burn it with the oxygen, you will get water. There is no emission, and there is a huge amount of energy that would be released. But we have a lot of challenges with the hydrogen, basically, because the infrastructure is not ready by any means. I mean, if you look at the hydrogen production, look at the hydrogen transport or hydrogen basically utilization, the infrastructure are very poor, and then there are a lot of challenges around them. So we need to look at these challenges and try to see if we can sort them out quite fast. So I will go through some of these challenges before I jump into the storage. So let us start with the hydrogen production. There are a lot of, I mean, like a rainbow of the colors for hydrogen as of now, brown color, the gray, the blue, the green and pink and others. But then the major ones as of now are blue hydrogen and the green hydrogen. So the blue hydrogen is basically going through the steam methane reforming. So you get the methane and then mix it with the water in the high temperature. So it's a steam, and then eventually we'll get CO2 and hydrogen. So you capture the CO2, and the process can be to some extent clean. So blue hydrogen, as of now, is has the largest capacity for producing hydrogen as a quite a mature technology. Green hydrogen, yeah, is the clean one, I guess. is the one that you basically electrify the water and split the water into the hydrogen and oxygen. I mean, it has its own kind of challenges. Where is it you're going to get the electricity? I mean, we believe that we can use the excess wind and solar electricity to produce green hydrogen. So I will go through these two technologies a bit in deeper now, and I will talk about the other color of hydrogen. So the blue hydrogen, I mean, it's not a very complicated kind of process. I mean, it is a bit energy intensive. So what we do, we basically get the methane, and then so you can see the chemical reaction here, the methane plus water, but this water is steam. So you need to find a way to basically vaporize the water, and that requires a lot of energy and heat, and then eventually we'll get CO and hydrogen. But then we are not happy with the CO, of course, and then we will go another shift and CO plus water, and then we'll give you CO2 and hydrogen. So now you can go towards the PCA or pressure swing adsorption technique, and then basically separate the hydrogen through the adsorption and then capture the CO2 through the chemical absorption technique, which is quite expensive, and then you have CO2 and hydrogen. So a bit complicated with a huge amount of CO2 emission that need to be taken care of with the extremely expensive CCS. On top of that, there have been a report that the amount of CH4, which is much more kind of toxic and more greenhouse gases than the CO2, is being released from the blue hydrogen generation. So you see that, yes, with the CCS, we reduce the amount of CO2, but in turn, the amount of CH4 that is getting released and leaked from this process is extremely high. So there have been a lot of discussion around this. You can look at this paper later. Equinor is not happy about this report, and they mentioned that, yes, there is a leak, but the amount of leak of CH4 is extremely lower than the estimation made here. So yeah, the discussion will be ongoing on this. So that's the problem with the blue hydrogen. What about the green hydrogen? Yeah, I mean, as we mentioned, basically is to electrify the water and then split the hydrogen to split the water into hydrogen and oxygen. So if you do this, it seems quite straightforward, but it's not. So one is that water doesn't have the electrical conductivity, so you need to put a bit of salt in it, into water for the electricity to split and go into the water. You put salt in it, then your cathode goes into degradation. You lost your cathode over time because of the salinity, and then you can shift to have the reaction in anode, but in that case, you need this proton exchange membrane, which is extremely expensive. I mean, the membrane is the one that the ion moves from one side to another. Because of the concentration gradient. Or, I mean, we can go to solid oxide kind of electrolyzer, but it still is extremely a high temperature kind of condition, so a bit energy intensive again. So as of now, the cost of the green hydrogen production is extremely high. It's much lesser than the value that it was a few years back, but it still is not the cheapest way of producing hydrogen. And on top of that, there is the efficiency is only 60–70%, and there is a huge amount of heat being lost from the electrolyzers that people need to look at. So, I mean, for instance, Lisa, as a district heating operator here, is interested to look at this heat with a temperature of 60 or 70 degrees, and they can see if they can use this heat to heat up the buildings nearby. So a lot of discussion around the green hydrogen and challenges there. The latest one, I mean, a new color basically is surfaced now, and that's white hydrogen. What is it? We call it the natural hydrogen. It's the accumulation of hydrogen in the storage site in subsurface. So what is it? I mean, there have been a lot of discussion around it. There have been a storage site, like a reservoir, like the reservoir that we have for oil and gas, and that there have been a lot of hydrogen in it. Yeah, so we have seen it, the biggest one in Mali. It has been in Brazil, Australia, and US, and even in France. So there is accumulation of hydrogen in a storage site, in a reservoir, in subsurface. How is it formed? How is it that is moving, is not getting absorbed by the microbes, why it's not leaking to the surface in many cases, how is it accumulated, what is the characteristics of the reservoir, we don't know completely. How it's formed, we believe that it's basically olivine that goes into the interaction with water and produce hydrogen, or the water itself goes into the hydrolysis. But I mean, we are not completely sure yet, because this kind of natural hydrogen have been seen in different kind of locations, in the sedimentary rocks, in the igneous and metamorphic rocks. So we are not completely sure how it's formed, and we're not completely sure how we can explore it. But that is quite a hot topic as of now, and everybody is interested to look into this white hydrogen. But going from the hydrogen production and all of the challenges of the hydrogen, we come to the hydrogen transport. What is the problem here? Hydrogen doesn't have, has a very low volumetric energy density. It's a small molecule, has a good energy density, but because it's small, its energy in terms of the volume is extremely low. So we can transport it in the gas form, but then the doesn't have the feasibility for the cost. So what is the best way? Then we liquefy it. But then, yeah, when you want to make hydrogen like a liquid, that's okay. Then you need to go through this process and then look at the phase diagram, which seems quite fine, but it's not, because this is in Kelvin. So what that means, it means that if you want to basically liquefy hydrogen, you need to bring the temperature down to 240, minus 240 or minus 250, which is extremely low. And bringing that to that condition is extremely complicated for the transportation. So that was there, and then on top of that, people say that, okay, what if we go with the liquid organic hydrogen transport, which is basically converting hydrogen to ammonia through the process that we call it Haber and Bush. And then so interacting hydrogen with the nitrogen, and generate ammonia, transport it as ammonia, and then in the utilization part, you crack it down back to hydrogen. I mean, yeah, it seems fine, but it's extremely complicated with extra cost and complications, yeah? So that is the hydrogen transport problem as of now. We want to make it efficient, but the phase diagram of the hydrogen make it a bit hard to do it. So then it comes from the hydrogen transport, then you want to store it. Why we need to store it? Because, I mean, as I mentioned in the other slides, hydrogen production through the electrolyzers has a lot of problems, is extremely expensive, and is relying on the wind and solar, which have the intermittency. Is it? So then you may have interruption in the supply of the hydrogen. So if you have a huge storage site where you can store the hydrogen, you produce it as much as you can when you can. You store it in a place, and then when there is an interruption in the supply, you provide the consumers with the hydrogen that you have stored. Is it? So that gives you a flexibility in this hydrogen economy. There are different ways of storing hydrogen, of course, the physical storage, material-based storage in metal hydrates, or chemical storage, and then the last one in a gigaton size is underground storage. Yeah. So when we say underground storage, we are talking about the gigaton kind of a space or a place for storing hydrogen. Others, yeah, they are good storage, but they don't really have the capacity that can be compared with something like a underground storage. So underground storage, we are concerned as of now with the salt caverns and then depleted gas fields. Salt caverns is the one that we have more practices and more experience about it, but if it leads a storage capacity. And then, of course, looking at depleted gas field. We are not looking at the oil field because this multi-phase flow is too much complicated and it's very hard to understand. So depleted gas field can be quite a huge solution, but a lot of challenges with that. And then, of course, cavern can be another solution, more experience, much better, but it has its own kind of challenges. So today I will go through the challenges of the caverns. I will introduce the caverns and challenges of the caverns as we move on. And I will leave the discussion about the depleted gas field to another kind of webinar. So geological hydrogen storage, as I mentioned, there are three of them, generally saline aquifers, depleted gas fields, and then the salts. I mean, you can see them here. Both of them, I mean, all of them basically provide a huge storage capacity. For salt is like a 500 1,000 cubic meter, and that the others, the saline aquifers and depleted gas fields, are much more larger than that. Saline aquifer is the most complicated one, but has a larger capacity. Depleted gas fields are fine. They have the infrastructure already there, but there are a lot of reactions that can happen in those sites that we are not completely sure. Okay, so salt seems to be a practical solution for storing hydrogen. But what is the salt? Why salt is the best? I mean, basically, you can look at the picture here. So we are talking about a thick layer of salt where you can create a hollow space through solution mining, and then that hollow space can be filled up with hydrogen. You can utilize it when you need it. Why hydrogen? Why salt are the best? I mean, they are quite tight, tighter than the others. And so there is a huge chance that the hydrogen would stay there. And then we have the practices of town gas storage. They didn't have that much of leakage, so hydrogen would stay there in the salt. And then it's a bit ductile formation. Ductile means it can deform. So every time you pressurize it, it deforms a bit. It doesn't crack. It deforms a bit. And then when you extract the hydrogen from it, then the pressure gets back to its initial condition. So it will give you the opportunity to inject hydrogen in it and then bring it back without having any kind of crack or leakages. And of course, because it's in a completely saline aquifer or saline environment, it basically gives you, I mean, a higher chance to have least consumption of hydrogen with the microbes. I mean, initially we thought that there is not that much of microbes in the caverns, but it seems that the microbes can still grow in that condition and consume hydrogen. I will talk about that in a minute. Okay, so yeah, so we talk about the salt and salt caverns. Both domal salt and bedded salt can be the solution as long as they have the thickness. So let me go a bit deeper into the caverns and cavern construction. So how we make the cavern constructed, we have a thick layer of the salt. Usually the thickness should be more than 300 meter. You start from the top, you drill through it, and you drill through the salt from the top, and they start circulate the water into the salt. Yeah, so we know that the water can dissolve the salt, yeah, but then you cannot use the fresh water, yeah, because of the regulation. We have to use seawater. It still can dissolve salt. It's not completely saturated with the salt, so seawater can still dissolve the salt. So we circulate the seawater into the salt, and then we start to dissolve the salt as we go further. And then the water, the brine that is accumulated here will be extracted out from the other side of the tube, and then from inside we inject the brine again. And then as time passes, we put a blanket on top. Blanket here is like a nitrogen. It just prevents the brine to go up, so it will basically distribute towards the wall, so you will create the foam that you want. Okay, so the blanket is just to protect the upper part. So this is the leaching initially, the solution, bringing everything back, and then eventually you cannot really bring everything to the surface, so there would be some sort of brine or a kind of debris left at the bottom of the caverns, which we call it a sump. Yeah, so the sump is the completely solid part that is stuck at the bottom, and on top of that you have a bit of layer of the brine. So eventually you will end up with a site like this. It gives you basically a bit of flexibility to store hydrogen in it. I mean, I have put some numbers here just in case if you guys are interested, and this is a case in China. I will talk about these as we go further. So integrity test, once you have created your cavern, you need to test the integrity. So there are two tests, the conventional tests that we need to do. One is to evaluate the integrity of the casing in the well, in the tubes, and then the other one is the integrity of the cavern itself. So if you want to basically evaluate the integrity of the casing, we use the packers, I mean, like a plastic things that can basically seal off this part, and you pressurize the top part. So when this part is sealed off, the pressure here grows. How much pressure? Before 70 or 60 or 70% before reaching the burst pressure of the casing, is it? So you pressurize and you hold. Yeah, so if there is any kind of leakages, the gauge on the surface will show you that there is a leakage, and you need to be careful with that. Once you are sure about the integrity of the casing, we pressurize the cavern itself. Again, this through the nitrogen. We use the packers, we seal off the bottom part, and we inject the nitrogen inside the caverns. Again, this test can be or must be done at least for 96 hours. And then through this, we evaluate the changes in the pressure through the gauge, and we evaluate the interface between the hydrogen and brine. So over time, we will see if there is any kind of leakages. So if the leakage per day is less than 50 liter, everything fine. If it is more than 50 but less than 150, we need to evaluate the case. But if there is a leakage of more than 150 liter per day, then the case will be rejected. So we need to evaluate and assess why there is a huge amount of leakage from the cavern. So construction of the cavern, and then the integrity of the cavern. So if you're sure about both of these, then you go into the operation. How we can operate? Again, remember that the hydrogen doesn't have that much of density. So what that means, it means that it doesn't really pressurize the whole hollow space that you have here. So the cavern often have a kind of height of 200 meter, and on average, again, the internal diameter of 80 meter, and then there is a bit of a space that you need to put on at the top and the bottom. So this often gives you like a 500,000 cubic meter of a space. But again, you cannot fill it totally with hydrogen, or you can fill it, but you don't get the pressure that you need. So you need to put something much more heavier into the cavern to pressurize it. So that's where you put nitrogen as a kind of conventional cushion gas. So cushion gas is the extra gas that we put in the cavern to pressurize it. So it's like a 10 to 50% of this whole cavern is filled up with cushion gas to give you a bit of pressure, and then the rest is hydrogen. Yeah. So when you pressurize the cavern, what you need to be careful is that you cannot really extract all of the hydrogen or all of the gas out of it suddenly, very fast. You always need to make sure that you leave some hydrogen or gas inside. Like in the best case scenario, I guess you can just only bring 50% of the whole stored hydrogen or the gas inside the cavern. Why we cannot bring all of it in the same time? Because you need a bit of pressure to hold the wall. So remember, the salt has a specific characteristics, like a creep, that I mean, eventually a salt, if it forms through the fatigue or different kind of geological condition, pressure and temperature, it can come, the salt will come and basically close your cavern. So if you have a pressure inside, then you can resist against the wall and then make the shape of the cavern as it is. Yeah. So the I mean, current practice, I guess, is to bring out of like a 20 bar, reduce the pressure by 20 bar per day, and then it has been successful, no problem so far. I think they will increase it to 30 bars soon. So the pressure management is very complicated in the caverns. Because the salt has the capacity to move. So you need to make sure that you always have a bunch of pressure inside the cavern to prevent the movement of the salt. So talking about that movement, these are some of the cases from different fields where the initial you can see the initial size of the caverns and eventually the size that has gone through the shrink or deformation induced by the salt. So remember, salt is a unique kind of material. It can go through fatigue and eventually start to deform and move, which we call it a creep. So a slow and continuous deformation under the stresses. I mean, we have the pressure solution, we have the dislocation creep. I mean, that goes into too much into detail of geomechanics of the salts. But what we need to remember is that you need to make sure that you handle the pressure inside the cavern very carefully. So pressure management is one of the kind of complicated steps of the managing the salt cavern storage site. So apart from the pressure management, which is a bit challenging, there are some other challenges that may come when you put hydrogen in a salt cavern. I mean, initially we thought that there are not that much of a problem, but it seems that there are as we go and explore more. So some of these problems are listed down here. It's quite interesting to read this paper. They have even quantified the amount of leakages. So we have chemical reaction due to microbial activities. I will talk about that in a minute. There is a chance that the leakage would be through the casing or interface of casing in the cement for the wellbore leak. I mean, through the wellbore. The cap rock on the top may go through the leakages, of course, if you don't really have enough cap rock there. Part of the hydrogen may go and dissolve into the brine because they are part of the brine or part of the sum that is left at the bottom of the caverns. And then, of course, there's adsorption loss. So there are a lot of, remember that as we go deeper inside in the formation in geological settings, the salt or halite, that's what we call it, is not completely pure. Yeah, so there are a lot of other layers that may come and contaminate the salt. So you may have calcite in it, you may have clay in it, you may have anhydrite. There are different interlayers or layers that can be part of your caverns eventually. And then these are not salts, so they will do their own behavior. So there's a huge chance that the hydrogen will go and will be lost through these layers because they have higher permeability and higher diffusion rate there. And then, so over time, you will lose part of the hydrogen going inside these kind of interlayers. Apart from that, I guess the challenge is to how to quantify these problems and then how to prevent them. So I will talk about two of these kind of challenges that we are, as of now, evaluating with one of my PhD students, and then I will close the discussion. So one of the major challenges that I mentioned is important is the geomechanical case or the salt creep that can take place in the caverns during the injection and withdrawal. So over time, as I mentioned, salt may go into the creep. But that is, I mean, I think even for the pure halite, we have completely understood to some extent, at least, that how it behaves. But as I mentioned, when we go deeper, in the geological settings, geological formation, like, I mean, in the coast of the Norway, there are huge salt, there's a huge capacity for the salt. The Zaxton salt is there, but it's quite deep. And then if it's deep, then the other interlayers or impurities that I mentioned, like anhydrite, carbonates and clays can come to the play. So the idea here that Jean Donald is evaluating as of now is to understand the behavior of these individual impurities. So we are looking at the anhydrite and we are looking at the clay. So you can see the salts, the pure salts, and the one with the anhydrite, and then here the salt with the clays. So what is the conclusion so far? We have understood that yes, anhydrite to some extent make it more ductile. Make the salt more ductile, which is fine. And then it will even give a better strength to the salt, which is still fine, it's good. But then will increase the creep tendency. It seems that anhydrite will increase the tendency of the salt to creep more. Okay, so we are still evaluating this, and that's the initial result. We need to do more tests and evaluate the condition under different kind of pressure and temperature. But it seems that anhydrite can make the geomechanical responses or the pressure management a bit complicated. And the last thing is the hydrogen loss because of the microbial. So Schwab et al. In 2021, I mean, you can look at that paper. They have studied different kind of caverns in Germany, and they took the sample from the brine from the bottom of the caverns, and they noticed there is a huge amount of microbes there. How the microbes goes there, we are not completely sure. It could be during the drilling operation or during the leaching operation, or the microbes or this holophilic microbes are already there in the structure of the salt, and then they just come out of it. We are not completely sure, but whatever it is, there is a huge amount of microbes there that they have the capacity to consume hydrogen and produce H2S or other gases like CH4. So two problems. One is that you are losing your hydrogen, and then two is that you're producing H2S, even in a small amount, that can cause complications for the environment, for regulation and utilization. Is it? So again, we have done some studies. Again, this is completely pure kind of modeling studies, and we will confirm this finding by doing some tests in IFP and in France. The idea and the concept, and then basically analyzing and understand the whole scenario, is that yes, the hydrogen consumption would take place, and then H2S will form. Again, the amount of H2S that will be generated is not significantly high, but remember that the threshold for H2S is extremely low if you want to use the hydrogen for fuel cells or others. So even a small quantity of H2S matters, in different kind of scenarios. So we will continue doing this kind of validation through the experimental study soon in France. Okay, so I mean coming to the conclusion, I hope that I give you a bit of kind of ideas about the challenges of this hydrogen economy. I didn't go into the utilization fuel cells because I think, I mean, this the discussion was going so long, but I mean, maybe later in another kind of discussion. So what the challenges, as I mentioned, we have a lot of challenges for production. Steam methane reforming is energy intensive, requires CCS, extremely expensive. It releases CO2 and CH4. Looking at the electrolyzers, they are extremely expensive. The membranes are expensive, produce a lot of excess heat. Efficiency is still 60 or 70%. Transportation, liquefied hydrogen is very hard to make because the phase diagram, the phase behavior of hydrogen, and then converting hydrogen to ammonia seems to be a bit complicated because, I mean, we have a bit of little infrastructure for hydrogen, but ammonia, we don't have anything. I mean, basically ammonia is for fertilizer. And then hydrogen storage, I mentioned that we have different approaches, the smaller scale, and we have the caverns and depleted field. I didn't go into depleted field, they have more challenges, but I have listed the challenges of the caverns that as of now we are trying to evaluate and understand. Okay, so and then these are the advantages and disadvantages of the hydrogen economy by itself. Yeah, so then this is the end of the discussion here, and I appreciate your attention, and if you have any question, please ask. Thank you very much.